Here's the glass. What's in the glass, gang?
Air.
Yeah, because what are we studying about today? Atmospheric pressure and air, right? What if we weren't studying about atmospheric pressure? Isn't it common to say, oh, there's nothing in the glass?
Yeah.
Then you take the glass and you say, there's nothing? And you can show a little ball, floats. Look at the air in the glass, gang. Can you see evidence of the air in the glass? See that? There's a little ball floating on the surface, and the surface of the water goes down because something pushed the surface of the water down. Begin with an A and with an R. Try it. Air. The air. And there's air in the glass. Yeah, there's air in the glass, gang. Any air in this room? Isn't it nice? Isn't it nice that there's air in the room? What if there's no air in the room? You'd be in trouble. Do you ever wonder about that, like you're breathing? You really need the air, right? In your nighttime, all of a sudden you think, wait a minute. If all the air molecules that are right here all of a sudden go somewhere else, and I go to take a breath, and there's nothing there, you're going to go out, you're going to check out. Aren't you glad the air is all around? How come the air stays near where your mouth is? Because it's being pushed by a pressure, and that pressure is due to the weight of air above us. Air have any weight? It turns out air has weight, a lot of weight if you talk about a lot of air. Okay? What's it go here? 1 cubic meter of air. It's about like this, huh? It's like about like this. Bam, bam, bam. 1 cubic meter of air, like a little small truckload, right? Has 1 1/4 kilograms, okay? That's about 2 3/4 pounds. So try this tonight when you go home. Open up the fridge. Now your fridge is about 3/4 of a cubic meter. Ask the people at the house, hey, the air inside there have any weight? What are they going to say? Yeah, it's got some weight. See that big grapefruit sitting there on the shelf? Does that have any weight? Yeah. Say, which weighs more, the grapefruit or the air? Take a guess. You got about 2 pounds of air in there. And if that grapefruit's less than a 2-pounder, then the weight of air in that refrigerator is greater than the weight of, it's greater than the weight of a dozen of eggs. A dozen of eggs weigh less than the air in an ordinary sized refrigerator. Now you're not noticing that weight of air. Let me ask you a similar question. Does water have a weight? Yeah, water kind of weighs a lot, doesn't it? If I handed you a great big bag of water, and I say, here, take this, and I put it in your lap, boom, and I ask you, does water have any weight? What are you going to say? You can say, yeah, it's got weight. Now let's suppose we go in a swimming pool, and you're under the water. And under the water, I take that baggie, and I hand you that baggie of water, and you grab it. And I say to you, does the water have any weight? And you're going to say, if it does, I can't feel it. What does a fish know about the weight of water? Nothing. Fish knows nothing about water. Fish doesn't know what it's like not to have water. See? We're the same way. We walk through the air all our lives, and we just take it for granted. We don't realize it's there. And we don't realize it's heavy. In your kid sister's room, the air in your kid sister's room has more mass than your kid sister does, if she has an ordinary sized bedroom. Air is quite heavy, 1 1/4 kilos for every cubic meter. Got quite a few cubic meters? You got more than a ton of air in an airplane to keep it pressurized. So air is kind of heavy, relatively heavy. And we don't notice the weight because why? We're in it. It's like the fish doesn't know the weight of water. Now air has pressure too. And air has pressure because of the weight. Let's look at the world. Here's the whole world here, okay? I'm going to draw the top of the atmosphere. How high should I go? You know what, gang? The top of the atmosphere is within the line that I drew. Because the air only goes up about 30 kilometers. And this is over 6,000 kilometers. So 30 parts in 6,000, gang, that's within the thickness of the chalk. So it turns out there's a very, very thin vapor of air hugging the world, and that's our atmosphere. It's not inexhaustible. Take a pool ball and put it in the fridge, huh? Let it cold. Open up the fridge, say, breathe on it. You get a little mist on it, right? You know how thick that mist is? About in proportion to the thickness of our atmosphere. We have a very, very thin vapor, 30 kilometers, not very much, you know. Compared to the world, 6,000 kilometers in radius. Eh? So it turns out that that thin vapor of air nevertheless has a weight and pushes down on us. It pushes down on us with a pressure. I'll show you an example of atmospheric pressure. See these cans? I put a little water in them. The water's boiling. And so are there fewer molecules in there now than before or more? Well, you can see them coming out. Stuff must be going out. So it must be that the pressure inside there is now realized by fewer molecules moving faster. Does that make sense? A few molecules moving very fast can exert as much pressure as a greater number of molecules moving slowly. So I'm reducing the number of molecules in there. What if I cool this very suddenly? Shall we try it again? What happened to these cans, gang? Let's try one more time. Look at these cans. Some people say, oh, the cans are sucked in. Cans ain't sucked in. What's happening to those cans? Check your neighbor. What's happening to those cans? Now, when you try that tonight, gang, you're going to want some explanation. A nice explanation will wait until we get up to heat and get up to condensation. When we get up to the idea that when steam condenses, okay, it loses volume. But for now, a first-order explanation would just be that in here there's heated air. And heated air means not so many molecules. But the pressure inside the can is actually a little bit more than the pressure outside. Can you see evidence of that? See the steam coming out. So the pressure's building up because they're moving fast, 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 yeah? What I do is I remove it from the heat, put it over here, and cool it. And when I cool it, what happens? The pressure inside goes down. How about the pressure outside? Some people would say, oh, the pressure outside must have all of a sudden increased. And you would say, no, it didn't all of a sudden increase. It's what it is all the time. And that humongous pressure pushed the can in because there wasn't the same pressure inside to hold it out again. We're going to come back to these cans again when we talk about condensation. Water changing to vapor, vapor changing back to water. Those ideas. But nevertheless, there's an enormous pressure due to the atmosphere, and I think you can see that now. Isn't it nice that you guys have air inside you? What happens all of a sudden someone takes the air outside of you? What are you going to look like? Huh? Here you are, here, gang. Isn't it nice you got the air inside you too, yeah? Okay? Okay. If I had a bamboo pole right here, and it went up about 30 kilometers, and that bamboo pole was 1 square centimeter in area, and I considered the mass of all the air that would fill up that bamboo pole, you know what all that mass would be? It would be 1 kilogram. 1 square centimeter up about 30 kilometers would be 1 kilogram of air. So that 1 kilogram pushes down with a weight, and it pushes down with a weight of 10 newtons. So it turns out the pressure due to the atmosphere here at sea level is 10 newtons for every square centimeter. Now we're talking about SI units, we talk about square meters. It's a little unwieldy. But it turns out there's about 10 to the 5th square centimeters and 1 square meter. And it turns out if you have 1 square meter, think of a great big sewer pipe, about 1 square meter in cross section. And that sewer pipe goes up 30 kilometers. You'd have about 10 to the 5th newtons pushing down. And that's the atmospheric pressure, 10 to the 5th newtons per square meter. And that's due to the weight of air above. That being the case, I got a question that you can answer. If you climb the top of a mountain and then measure the atmospheric pressure, would it be less, the same, or a little bit more? You be checking the neighbor. Hey, gang, let's suppose you had a pet lobster, and the pet lobster is way down there in the deep briny there, and the pet lobster says, you know what, it's just too much water pressure. And someone says, well, why don't you climb that ledge, and when you get closer to the surface, the water pressure will be a little bit less. Would that be a true statement or a false statement? That'd be a true statement. And what do we live in? We live in an ocean of air. So we've got a pressure acting down on us. When we climb a mountaintop, aren't we getting closer to the surface? Now, there isn't a sharp, sharp surface with the air like there is with the water. Well, we're getting, it kind of peters out and peters out, doesn't it? In fact, you guys know if you go about 3.5 kilometers high, is it 3.5 kilometers high? It's in the textbook. I forget the figures. Yeah, 5.6 kilometers high, gang. You got half the air underneath you. And you go up to, what is it, 30 kilometers high. Okay, that's about 19 miles. 30 kilometers high, 99% of all the air is underneath you. So when you're flying in an airplane and the airplane pilot says, hey, we're 40 kilometers high, honey, he's made a mistake. You got nothing to ride on up there, right? The wings aren't going to ride in the air. You can run out of air. The air doesn't go up that far. Here's kind of a neat little deal here. This is called the unicorn experiment. Little bottle, piece of paper, match, light the paper on fire, fire burning, I cut off the oxygen, and when I do that, follow me, gang, I'll make your crops grow. What's going on here, gang? Oh, gosh. Well, this is my new style. I'll see you guys down the wave tonight, all right? A little tattoo there. What's going on here, gang? Huh? The heated air cooled, and when the heated air cooled, what happened to the pressure inside? Went down. How about the pressure outside? But why does it hold to my head? Why? How many people say, well, it has something to do with air, but there's probably no reason for that? Huh? It's sort of like this. What are these devices here? You know what this is. This is a physics experiment, right? How come it's sticking, gang?
The air inside. The air on the outside.
It looks like we all are going to have one of these, gang. What's going on there, huh? Why? How many say, oh, there's probably no reason for that? Isn't the air pressure pushing against the side there? Isn't the air pressure inside pushing back out? But not as much, because I squashed some of the air out. And when I squash the air out, it starts to come back, it reduces the pressure inside. So I have reduced pressure inside, but atmospheric pressure outside. So I have more pressure pushing here than in there, and so it stays. Isn't that neat? You could explain this to someone. Everyone knows this will happen. Someone, oh, it's because of suction. All right, okay, it's because of suction. Now explain the suction. And we can do it, can't we? More pressure on one side than the other, and, huh? Yay. So a toilet plunger makes a nice suction cup, gang, but you don't have to have a toilet plunger, because this is like a suction cup too. You know what this is? It's just a regular piece of rubber, a piece of floppy rubber, and I've got a hook on it. I'm going to put it on the stool. I'm going to lift it up. I'm going to lift it up. Would you lift it up, please? Lift it up by the hook. Yeah, all right. Like a suction cup, gang. What's happening there? When this pulls up, can you be explaining such a thing to your friend? Yeah. Glass filled with water, yeah? Okay, where's my cards? Take a card. Huh? Okay, look at that. No problem. No problem. Still no problem. HC. Somebody say, wait a minute, man. Ain't there water pushing down with the pressure? Yep. Well, then shouldn't that pressure push the card away? Nope. HC. And your neighbor says,
Say there was a little air bubble on that. Can it still hold?
yeah, what if there's air in there, gang? Does that help it to stay or not help it to stay? Yeah. Let's try it with like air in there. Yeah, okay. Okay. We want it filled with water, yeah? Now, some people would say, why doesn't the water pressure push the card away? And your neighbor said, because the air pressure pushing up on the card. See, let's look at this on the board. There's water pressure pushing down like that. But there's an air pressure pushing here. Air pressure pushing here, air pressure pushing here. I'm denoting pressure with these forces. That would really be the force due to the air pressure. You can kind of see that. But there's more up than down. Because in here, that water pressure is not pushing down as hard as 30 kilometers of air are. 30 kilometers of air pushing down a lot harder on that card than the water. Now, I'd have to make the water taller. Some of you people know how tall a water column would it have to be to push down just as hard as 30 kilometers of air. Some of you people know because you read the text. Check the neighbor and see if your neighbor knows. How many meters high of water will push down just as hard as 30 kilometers of air? Okay, gang, what's the answer? How tall a water column would you have to push down just as hard as the atmospheric pressure is pushing down? 10.3 meters, that's right. 10.3 meters, that's about 30 feet. About 30 feet high. If you have a 30-foot high column or 10.3 meter column of water, that's going to push down just as hard, and that card will not stay there. It'll push away. Or if I have some air pressure on back here, if I have atmospheric pressure on back here, that atmospheric pressure plus this will push that away. Unless this starts to come down and reduces the pressure enough such that it won't. Sometimes you can get an air column and the liquid in there. That's if the card starts to pucker, air pressure reduces, and you still have less pressure pushing down than you have here. Then, of course, there's a little surface tension that'll help you in there, too. But it's kind of neat how that works. Now, if you want to make an instrument to measure air pressure, you could have one of these 10-meter high things of water. But better than use water, it's better to use something more dense, so your height won't have to be so high. And what's the densest liquid we know of, gang? Mercury. Mercury is 13.6 times as dense as water. That means the column of mercury would only have to be 1/13.6 as high. And 1/13.6 of 10.3 meters turns out to be 0.76 meters, turns out to be 76 centimeters, turns out to be 760 millimeters. And so when you're talking about atmospheric pressure in terms of millimeters of mercury, that's what you're talking about. See, because if you have like, all you have to do is take a dish of mercury, and that mercury will glug right out there. And when that mercury column is 760 millimeters tall, well, it's about like this, huh? Okay. When it's that tall, that's going to push down on the surface with just as much pressure as the atmosphere outside. And so it will stand right there. Now let me ask you this common sense question. What if the atmospheric pressure increases? What's going to happen to the mercury? It's going to push it right up further, isn't it? It's going to push it up further until it's pushing down with the same pressure that the atmospheric pressure is exerting. Isn't that true? And so what would happen if you took this barometer, this is a barometer now, right? Let's suppose you put it in an elevator and took a ride to the top of a skyscraper. What's going to happen to the reading? It's going to go down. You guys ever feel in some of these skyscrapers going up, you can feel the reduced pressure. You really can. And that barometer would pick it up. And so the barometer would fall the higher you got because there's less air up there, less air pressure. Kind of makes sense, doesn't it?
What's above the column of mercury?
Question?
What's above the column of mercury?
Begins with a Z.
Zip.
Zip, nothing. A vacuum. Maybe a little bit of mercury vapor, but in a sense, nothing. There's no air up there. See, because you would make this thing by filling it up completely with air. I should have mentioned that. I mean, you'd make this by filling it complete with mercury, dip it over, and the mercury will glug, 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 glug out, and what's in the top? Nothing, a void. So that would be like a vacuum, maybe a little mercury vapor, but certainly not air, because how did the air get there? Kind of see that, gang? I mean, I could take this. Suppose this was 10.3 meters tall. I'll bring it up like that, and all of a sudden it would start to drop. See, if that's like this, let's suppose 10.3 meters here, then there'd be nothing there. So it'd be a void. Maybe a little water vapor, yeah? But there'd be nothing. It wouldn't be like there's air there. There's nothing there. Oh, I see that, yeah. Here's something kind of nice. You've seen people do this. Is this a big deal that I can pour water from one container to the other? How many people say, wow, look at that! Ooh, man, poured the water from one container. Am I glad I came today? Huh? That's no big deal. You want to see something that's kind of a big deal, okay? Here's what I want you to do tonight. Take a glass of water. Tip it over. Take a glass of air. And pour the air into the water. And ain't that nice? Huh? You like that? You glad you came? Huh? Is physics fun? Physics yum yum or yuck yuck? It can be yuck yuck. But it can be yum yum too, yeah? Okay. You ever wonder about how they build, how they pour concrete down under the river to make the bridge? Do you ever wonder about that? I mean, you see these bridges in the water, right? And down, and it's all how do they get the concrete underneath there? And they got workmen go down there. Do you know what they do? They have a great big thing like this. Okay, this is little tiny guys like this. And they bring it down, down, down like that, right down to the bottom. And the other guys are down there working. But you know what? As I keep pushing this down, 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 it turns out the pressure gets squashed. Not the pressure, the air gets squashed. And it starts to get more and more compressed. This is not deep enough that you can really see the difference. But if I push it 10.3 meters down, then the water pressure will be just equal to the air pressure at the top. So you'll have twice the total pressure, 10.3 meters under. And that's going to squash the air up to half size. And that brings us up to Boyle's law. Boyle's law, named after a dude by the name of Robert J. Law. Okay, we're learning these things, all right? And Boyle's law just says that pressure multiplied by volume at any one point will equal pressure times volume at another point. So get twice the pressure, you'll get twice the volume. Yeah, what did I say? Oh, twice the pressure would be half the volume. Very good, Lee. Sometimes I goof a Rooney a little bit, right there. But does that make sense, gang? So you get twice the pressure. It's going to squash that stuff up, so the volume be half as much. Huh? What if you push, so you got 3 times the pressure? Then the volume will get scrunched up to how much? 1/3. A third. How about, oh, I don't know if you can do this. Let me try. 7 times the pressure. Okay, no, I shouldn't say 7. No, let's say 5. 5 times the pressure. A fifth, right? How about 9 times it? How about, all right, here's for the A students. 7.9 times the pressure. Gotcha. How many people say, you ain't got me, honey? It's 7.9 of the volume. Show of hands. Front row. Next time. Last time we talked about a problem, gang. And the problem was where we had a balloon. And the balloon is weighted down. So it just barely floats in the water. If it's just barely floating, what's the density of that balloon and weight compared to the water? Equal, isn't that right? So I could say mass per volume, weight per volume. The idea, the concept is the same. Your question was, when you push that balloon underneath the water and then let go, what's the balloon going to do? And all you guys reasoned it out, and you said, hey gang, if it was a piece of wood, you pushed it under, what would it do? If it just is the density of water, it would stay there. But it's a slight bit less, it would come back up, right? How about a balloon, though? Balloon going to sink, stay where it is, or come back up? Sink. Let's make a hypothesis that it does sink. Let's think about this logically, okay? Kind of scientifically. Let's say it sinks. If it does sink, if it does, logic now, what would have to happen to the density? It would have to be more? Is that right? Yeah. It'd be more. Okay. How many ways can you make the density greater? How many know that it's 2 ways? And how many know it's 2 ways because the definition of density tells you? Okay? So if you make the balloon heavier, will you make it more dense? Yeah. So if you can think of any reason when you push it under that it becomes heavier, then it would become more dense? Then the hypothesis that it sinks would be true? Okay. Can you guys think of any reason why it would be a little heavier when you poke it under the water? If you can, it sinks. Any takers?
Shrinking the volume, decreasing the volume.
You're talking about volume. I'm talking about weight. I only think about one idea at a time. I got friends that think of only one idea at a time, period. And with that one idea, they'll take up arms, they'll do everything. My God, they don't think about the other side, you know what. But hey, let's look at this. Weight. Does the weight increase, gang? Doesn't it get closer to the surface of the center of the world? Huh? Huh? Yeah, but it's under the water. The water's gravitating it back up too, yeah? It turns out the weight doesn't change, at least not at the first order. So if the weight doesn't change, the density doesn't change, therefore it doesn't sink. So it doesn't sink. Isn't that neat? So hypothesis number 2 is that it floats. Shall we go on to flotation? What's wrong with my reasoning? Like most people in the world. What's wrong with my reasoning? I'm not considering the whole story. And the whole story is not only weight, but volume. Ah! So what would have to happen to the volume if the density is going to get more? How many say the volume would have to get bigger too? Everything gets bigger. You may want to make something bigger, everything, come on. The volume is going to get smaller. And when you push it under, can you think of any reason why the volume should scrunch up smaller?
Greater pressure, water pressure.
Can you?
Depth.
But the pressure of the water is only going to be a little bit more.
Well, that's more. That's more than what it is now.
That's right, and it's going to make the volume a little bit less.
Right.
And if the volume's a little bit less, the density is going to be a little bit more. And if the density is a little bit more, it's going to sink. So it sinks. Yeah. We got to get that one right, gang? Huh? Okay. Isn't that true too of you when you're swimming? When you're swimming down, doesn't the density, doesn't the pressure push you into? And don't you become more dense too? And don't a lot of people that find they can float to the top a few feet under get way down there? Gang, you sink. You know? When you snorkel, yeah? Snorkels are about this long, yeah? You're snorkeling away, okay? You get it pointing up, huh? There's a water level right here. You can breathe that all right. That's no problem. How about you make it longer? How about you take your snorkel like this? So I think I'll go a little deeper. I'm not into scuba tanks, honey. I'm just going to take this and go way down. Now, can you go that deep? Huh? What happens you're that deep, gang? You got a lot of water pressure pushing in on you. And what's that water pressure pushing on your lungs? And what's that water pressure going to do to the volume of your lungs? Scrunch them up, right? Okay. So the pressure's going to be more in there, right? Now you got more pressure in your lungs than up there. Which way is the air going to go? Someone go. You can't go. I was telling you about this the other day. I got to down about this far. I got to about here. I could go this deep, and when I was that deep down here, that deep, I could just barely breathe. And any deeper, ooh, couldn't do it. So that's what that's all about. That's why you have to have pumps at the surface, or you have to bring a scuba tank with you. And with that scuba tank, that's regulated so the deeper you go, the more pressure it feeds into your lungs. It's got a little regulator. And it keeps the pressure in your lungs the same as the pressure of the water outside, without your lungs having to be scrunched down, so they blow up. What's the first thing that scuba types will tell you if you're at the bottom, you got a lung full of air, and you abandon things and you go to the top? What's the first thing they tell you not to do? What's the thing that people tend to do? They say, oh, I got to get all the way to the surface. I better save all I got, right? So you what's going to happen to you, gang? Yeah. Just as this balloon sinks deeper and deeper and gets smaller and smaller, if it's at the bottom, very small, and now starts to come to the top, what's going to happen to the size? What if that's you holding your breath down there? What's going to happen to your size? Called rupture city, honey. Rupture city. You're going to be in trouble. So they tell you, let your mouth open and let the air come out. And it keeps coming out. Where'd all that air come? You got compressed air down there. And you let the air come out as you rise. So you don't all of a sudden blow up like this and really hurt yourself. You want to see what an exam question would be on a balloon question like this, guy? Here's an exam question on that. As this balloon starts to sink, will it sink all the way to the bottom? How many people say, oh, no, it'll get down to a certain elevation like everything and kind of just stop? Even rocks, man. You throw a rock overboard, it'll finally go down, and the pressure will get so much it'll just kind of hang there. All those scuba diver types, you ever done that? They say, watch out for those rocks, honey. Rocks hanging in the air. When you throw a rock over, does it sink all the way to the bottom? And will that balloon sink all the way to the bottom? Okay, now here's the question I got to ask you. As this balloon sinks deeper and deeper, the buoyant force that acts on the balloon will actually become more and more. No. The buoyant force that acts on the balloon will actually become less and less. No. The buoyant force that acts on the balloon will stay the same all the way down. Check your neighbor. What's the answer, gang? What's going to happen to the buoyant force as you sink deeper and deeper? What is it? How many say the buoyant force will get more and more because you're getting deeper and deeper, more and more pressure? Show of hands. How many say, no, it stays the same? One thing I learned, everything's the same. The cry of the ignorant, oh, everything's the same. How many say, no, it'll get less and less? How many say, I'm not sure, but I'm not going to stick up my hand and make a darn fool of myself? Okay, we'll ask that question another time. Hey, we talked about wood floating, and you guys know why wood floats, because the buoyant force acting up equals the weight acting down. Isn't that true? In fact, isn't it true that anything that's submerged in any fluid will displace a weight of fluid equal to the no. How's that go now? Anything submerged in a fluid will be buoyed up by a force equal to the weight of the fluid. Now, we said fluid and not liquid. Why? How about someone says, I can see why a fish doesn't sink, and I can see why a hunk of wood doesn't sink, but I don't see why that air-filled balloon doesn't sink. Wait a minute. If you see one, you've got to see the other. Because the air-filled balloon is displacing air, yeah? And isn't there a buoyant force on the air-filled balloon? And if that buoyant force is more than the weight of the balloon, what will the balloon do? It'll go up. If that buoyant force is equal to the weight of the balloon, what will that balloon do? Stay there. And if that buoyant force is less than the weight of the balloon, it will sink. So if I take a balloon, I blow it up with air, and I let it go, whoom, it sinks. Why does it sink? The balloons you see at the end of the string at the circus, honey, those are filled with helium. Okay? But why is it you blow your own up with air and it sinks? How about that air, gang? Is that air more dense or less dense than the air outside? It's a little bit more dense. Do you know why? Because the stretched rubber is tending to compress it. So it's slightly compressed. So it's more dense than outside. That means its volume of air will weigh more than the equal volume outside. It's going to sink. But you use helium. The helium is very, very light. Not as heavy, huh? Each molecule is not as heavy, so it is not as dense. So the helium-filled balloon is simply lighter than the buoyant force, and up it goes. But here's a point, too. We get that buoyant force because of a difference in pressure. Is that right? A difference in pressure? Always more pressure on the bottom because it's deeper than the top? So I got a question. If someone says to you, hey, I understand the atmospheric pressure keeps getting less and less the higher you go. At the top of a mountain, there's less air pressure. In cities like Mile High Denver in Colorado, there's less air pressure than in low places like at sea level. They say, I understand that. And they say, but would there be more air pressure here compared to here? Is there more air pressure where my lower hand is compared to here, gang? It turns out, if a helium-filled balloon this size will rise, then that is evidence that the pressure here really is more than the pressure here. See, Archimedes' principle never told you why there was a buoyant force. It was a nice little way of telling how much buoyant force. But the reason you get a buoyant force, when you're swimming and you're buoyed upward, remember, this part of your body is deeper than this part. Or a balloon. This part is deeper and more pressure than this part, and so up the balloon goes. It turns out if you move that air, if the air is in motion, then you get a nice effect. Moving air doesn't push with as much pressure. If I have some slow-moving air traveling over the top of this table, here's some molecules. Hear that? I'll do it again. That's air pressure. Now we'll have the air moving faster. In which case was there more pressure? When air moves fast, the pressure it exerts is less. This little analogy here has a weakness, but it'll allow you to understand that a little bit. Let me show you what I mean. I have here an air jet. And I'm going to take a ball, and I'm going to put the ball in the air jet, and air is going to pass faster on one side of the ball than the other. Now, where the air is moving faster, what's going to happen to the pressure gain? And where it's slower, it's going to be, and that means there's going to be a pressure difference, and that might act on the ball and hold it up. Follow me, I'll make your crops grow. Okay? Okay. Okay. Now we got one more, I think, in here. That's a little one. We gotta have another one here. Well, you kind of get the idea again. Now, what's going on there? Do you ever wonder why an airplane stays up? An airplane? Okay. An airplane wing is curved. The air moving across this part here is going faster than here. And you might think because it's going faster, it's going to push more, but it doesn't. Okay? It's like this. If you have air traveling across the top of a wing, the air will move faster over here, if it keeps up. If you have this air here and it gets over here, it's gone a greater distance in the same time. Turns out the air will move faster over there. Water flowing down in a brook. Here's a top view of a brook, and all of a sudden it gets narrow. When the water is coming down here, going through the narrow part, it will speed up. Or going through across these points here, it will speed up. Even if you take this off and let it go, the water will speed up as it goes through the narrow part. Air coming across here, let's suppose we have like a constriction here. The air would have to speed up and going through here, even if the constriction is not there. Air will go faster over the curved part than this part. And when it goes faster, it doesn't bump in as much as when it's going slower. Like if this is my wing, and air's going over the top part, and it goes like this, and over the bottom, more pressure on the bottom. Now, it's not quite that simple, because when I did this, I've got twice as much air going across there, too. It's going twice as fast, I've got twice as much air. Over here, I've got, is that right? To say air is going twice as fast, to say you must have twice as much, if you have the same density. So at least it's nice to think of going fast, not hitting so hard, going slower, hitting harder. That helps you to remember that slower moving air pushes with more pressure than faster moving air, and that's what gives you a lift. Now, that's Bernoulli's principle, and birds fly that way too. Birds have their wings curved, and the air moves a little faster over the top than the bottom. I got a question for you. Bernoulli was in the 1700s. Do you know what birds did before the time of Bernoulli? Yeah. Birds couldn't fly. They couldn't fly. Birds were ground struck. Okay, walking along the ground. That's why they have legs. You ever notice all birds have legs? Okay? Show me a bird with no legs, okay? And then along came Bernoulli and boom, flight. And now birds can fly. So why? Physics, gang. Good for you.